Hey everyone, welcome back. So today I have two probability questions prepared for you, both of which will require some thinking. They're not exceptionally hard, but I encourage you to try them since their solutions are very beautiful. So let's get started with the first one. For the first question, you roll a fair n-sided die repeatedly and sum the outcomes, and you're asked to give the expected number of rolls until the sum is a multiple of n for the first time. And so go ahead and try this. For those that maybe need a little bit more help, I also have a hint. If you don't want to see the hint, then pause the video right now and try to solve it. And if you do, here's the hint. So the hint is that for a discrete random variable x defined on the positive integers, the expectation of x is the infinite sum of the probability that x is greater than or equal to I. Okay, so if you've had to think, let's first show why this is actually true. So the expectation of x, we can write this as 1 times the probability that x is equal to 1 plus 2 times the probability that x is equal to 2 plus 3 times the probability that x is equal to 3, and so on. And so let me try to write this in a different way. So we'll have the probability that x is equal to 1 up here, and then I'll write the probability that x is equal to 2 twice here, but I write it below each other, so like this. And I guess I'll add a plus here too. And then same thing for the probability that x is equal to 3. So x is equal to 3 plus probability that x is equal to 3 plus the probability that x is equal to 3. And remember that this keeps going, so we'd have here plus, plus, plus. And so this right here, this is just the probability that x is greater than or equal to 1 if this keeps on going forever. Same thing for here, this is just the probability that x is greater than or equal to 2. And then up here we have the probability that x is greater or equal to 3, and so on. So you can see that this actually holds. If we sum all these up, we get the infinite sum from I equals 1 to infinity of the probability that x is greater than or equal to I. So that's why this hint is true. Okay, so now that we've proved the hint, let's define xi just to be the number that we get on the ith roll. And then we can also define sk to be x1 plus xk, so just the sum of the first k rolls. And lastly, we'll also define x to be the number of rolls until the sum is a multiple of n for the first time. Okay, so to solve this problem, we're going to be using the hint. And to start off, we want to find the probability that x is greater than I. Not greater than or equal to I, but greater than I. So this is equal to the probability that n does not divide s1, that n does not divide s2, and all the way up to n does not divide si. Why? Because we want x to be greater than I, which means that n has to divide some si for sk greater than si. So n cannot divide any sums up to I. And so if we look at this term right here, we can actually split this up into the probability that n does not divide s1 times the probability that n does not divide s2, given that n does not divide s1, times the probability that n does not divide s3, given that n does not divide s2 and n does not divide s1, and so on. So all the way back here we'll have the probability that n does not divide si, given that n does not divide all the other, like si minus 1 and all the others. But now, for example, let's look at this term. The probability that n does not divide s3, given that n does not divide s2 and n does not divide s1. Well, if n does not divide s2, then it already means that n does not divide s1, because if n divided s1, then we would have stopped playing, like the game would have been over already. So we can actually rewrite this as the probability that n does not divide s1 times the probability that n does not divide s2, given that n does not divide s1, times the probability that n does not divide s3, given that n does not divide s2, just that without the n does not divide s1, all the way to the probability that n does not divide si, given that n does not divide si minus 1. So really what we've done is we've gotten rid of all the other conditionals at the back here, since we don't really need them. They're already encoded in this term. And so this is just the probability that n does not divide s1 times the product from k is equal to 2 to I of the probability that n does not divide sk, given that n does not divide sk minus 1. Okay, so I've cleaned up this expression a bit, but again, we can see that the probability that x is greater than I is just the probability that n does not divide s1 times this whole product of the probability that n does not divide sk, given that n does not divide sk minus 1. And so let's think about what all these terms are. So the probability that n does not divide s1, well, you'll note that s1 is just x1, since s1 is the sum of the first x1, which is just x1. And so the probability that n does not divide x1 is just n minus 1 over n, since the only number that actually divides n out of n numbers is just n. So for all the other n minus 1 numbers, they don't divide, or n doesn't divide them. And so if we look at these other terms, we can actually see that the probability that n does not divide sk, given that n does not divide sk minus 1, is also n minus 1 over n. Why? Well, if n does not divide sk minus 1, then n is equivalent to some p mod n, for some p less than n, greater than or equal to 1. And so in this case, there's also only one number that we can roll to make n divide sk, which is actually precisely n minus p. And so for all the other n minus 1 numbers, if we roll any of those n minus 1 numbers, n will not divide sk. So this probability is exactly n minus 1 divided by n, the same as this probability. And so to write this down, this is just n minus 1 divided by n times the product from k equals to 2 to I of n minus 1 over n. But this is just n minus 1 over n to the power of I, which is just 1 minus 1 over n to the power of I. And so since we know that the probability that x is greater than I is just 1 minus 1 over n to the I, we can calculate the expected value using the hint above. We know that the expected value of x is the infinite sum from I is equal to 1 to infinity of the probability that x is greater than or equal to I. But this is just the infinite sum from I is equal to 0 to infinity of the probability that x is greater than I. And so this is just the infinite sum from I equals 0 to infinity of 1 minus 1 over n to the I. Okay, and now this is just an infinite geometric series. You'll know that the starting term, a0, is 1 minus 1 over n to the 0, which is just 1. And then the ratio is 1 minus 1 over n. And so if you know your formula for the infinite geometric series, you know that this is just equal to a0 divided by 1 minus r, which is just 1 divided by 1 minus 1 over n, which is just n. So the answer is actually pretty simple, and it makes sense. The expected number of rows until the sum is a multiple of n is just n. Okay, so let's try to simulate this solution as well. We'll import random, then we'll also define the multiples of n function, which takes in two parameters, so the number of digits on the dice, and then n is just the number of trials. So we'll say dice numbers is just a list of range from 1 to number of digits. We actually have to add 1 here because it doesn't include the last number. And then we'll say number of rows is equal to 0. This will just keep track of the total number of rows. So we'll loop through the n trials, n, there we go. And we'll say s is equal to 0. S will just keep track of the sum of all the rows. And then rows is equal to 0, and also we'll say done is equal to false. And here we'll say while not done. And we'll say x is equal to random.choice from those dice numbers. We'll increment the rows by 1, plus equals to 1. And then we'll also add x to s. And then down here we can say if or if the dice numbers, if the number of digits divides s, this is equal to 0, then we can say done is equal to true. And so down here we can just add the rows to the number of rows. There we go. We can add the rows to it. And then down here we can just print expected number of rows. We can just say number of rows divided by n. Okay. You can print another line to make it look nice. Oops. And then down here we'll just say multiples of n. We'll give it just a normal six-sided die, and we'll run this for 100,000 trials. Okay, and so if you run this, we get about 6, which is what we calculated. We can try a different set. We can try 10 dice, or a 10-sided dice, and we get 10 as well. So seems to be right. So for our second problem, we have 8 boys and 7 girls that went to the movies and sat in the same row of 15 seats. And assuming that all the 15 factorial permutations of their seating arrangements are equally likely, we're asked to compute the expected number of pairs of neighbors of different genders. So take a while to think about it, and I'll give you the answer right away. Okay, so to solve this, let's take 14 random variables, x1 through x14, and define xi to be 1 if the genders on seats I and I plus 1 are different, and 0 otherwise. And so as you can see, we just want to find the expected value of the sum of I is equal to 1 to 14 of xi. And so by linearity of expectation, this is just the sum from I is equal to 1 to 14 of the expectation of xi. And notice that since all these xi's are symmetric, they're basically the same. E of xi is E of xj. It's the same for any xi and xj because they're all symmetric. And so all we have to do is calculate E of xi for some arbitrary I, and then we can just multiply by 14 to get all of them. And so E of xi is the probability that xi is equal to 1, which we can split up into the probability that xi is equal to 1, given that a boy is in seat I, times the probability that a boy is in seat I, plus the probability that xi is equal to 1, given that a girl is in seat I, times the probability that a girl is in seat I. And so the probability that xi is equal to 1, given that a boy is in seat I, is just the probability that a girl is in the seat I plus 1. And since a boy's already sat in seat I, we know that there's 7 girls left and 14 people in total left, because already one of the 15 people is taken by the boy in seat I. So the probability that xi is equal to 1, given that a boy is in seat I, is just 7 over 14, which is just the probability that there's a girl in seat I plus 1. And then the probability that a boy is in seat I is just 8 over 15, since there are 8 boys and 15 people in total. And then for the probability that xi is equal to 1, given that a girl is in seat I, well, it's exactly the opposite. It's 8 over 14, since one girl is already taken in seat I, and then the probability that a boy is in seat I plus 1 is just 8, since there's 8 boys left, divided by 14, the total number of people left, times, then the probability that a girl is in seat I is just 7 over 15. Okay, and so we have a little bit of cancellation going on here. This is just 1/2. This is also just 1/2. So this is equal to 1/2 times 8 over 15 plus 1/2 times 8 over 15, which is just 8 over 15. And so the expectation of xi is just 8 over 15. And so up here, we know that the expected value of all these, of the sum, is just the sum of the expected values. We have that this is equal to 14 times 8 over 15, which is just 112 over 15. And this is actually equal to about 7.47. So let's see if this is actually right in a simulation. Okay, so let's start by importing random. We'll define a helper function first called count opposite genders, which takes in a list. And this list will just be a list of boys and girls, like as strings. So we'll define s is equal to 0, and then we'll say for I in range len list -1. There we go. Just say if list I does not equal list I plus 1. So if neighboring people aren't of the same gender, we'll increment s by 1. So we'll just return s. Okay. And so now we can define the seating arrangements function that takes an n as the number of trials. We'll say people is just 8 boys and 7 girls, so that's 1 boy, 2, 3, 4, 5, 6, 7, 8. And then here we have 7 girls, so that's a girl, and we'll have 6 more. 1, 2, 3, 4, 5, 6. Okay, let me remove this comma. Okay, and so here we have, we can count the number of opposite genders. This will just keep track of the total number of opposite genders. Then we can loop through the n trials. There we go. And we'll just shuffle those people. There we go. And then we'll just say and opposite genders. We'll just add the using that function that we made. we'll just count the number of opposite genders and add it to this variable. And so out here, we can print the expected number of opposite genders. We can say n opposite genders divided by n. And let's print this again to make it look nice. And then here, down here, we can say seating arrangements. Let's run this 100,000 times. There we go. Okay, so if we run this, we get 7.46, 7.48, 7.47. So our math seems to be right. Okay, so thanks for watching. For those who were able to solve those problems, congratulations. They're pretty hard. And then if you enjoy this content, please consider subscribing and maybe liking the video. And other than that, I'll see you guys next time.